Hey there, fellow curious minds. Today we're diving into a mind-bending topic that will make you question everything you thought you knew about time and space. Get ready for a wild ride as we explore the fascinating world of special relativity and its impact on our understanding of the universe. Imagine a beam of light, a single photon, traveling across the vastness of space. Now here's the mind-blowing part. This photon can traverse 1 billion light-years in an instant, experiencing no time at all along its journey. How is that even possible? Well, buckle up because we're about to dive deep into the rabbit hole of special relativity and uncover some truly mind-bending insights. You see, time is not this universal constant that we often take for granted. It's not like a background that every object in the universe shares. No, time is a slippery concept that depends on speed, location, and the path an object takes through spacetime. It's almost like time is a personal experience, unique to each entity in the cosmos. Let's consider an experiment with two identical atomic clocks. These clocks are synchronized and then separated, with one staying put and the other embarking on a journey aboard a fast aircraft. When they meet again, the traveling clock has recorded less elapsed time compared to its stationary counterpart. It's a tiny difference, but with modern atomic clocks, we can measure it with precision. This phenomenon, known as time dilation, is a direct result of special relativity. A moving clock runs more slowly than a stationary one when observed from the same reference frame. It's almost as if time itself is playing tricks on us, bending and twisting to accommodate the laws of physics. Now here's where things get really interesting. Light, that ubiquitous messenger of information, refuses to follow the ordinary rules of motion. Its speed in a vacuum remains a constant for every observer, regardless of their relative motion. Whether you're sitting still or hurtling through space at incredible speeds, light always travels at the same speed. Albert Einstein, the genius behind special relativity, recognized this fact in 1905. He realized that if everyone measures the same speed of light, observers moving relative to one another cannot agree on both distance and time. These measurements must adjust to keep light speed constant, and that's where things get really trippy. Hermann Minkowski later provided a geometric foundation for special relativity. He described space and time as a single four-dimensional structure called spacetime. Within this framework, faster motion through space results in slower passage through time. It's almost like time is a trade-off for speed, a sacrifice we make as we venture further into the cosmos. To visualize this effect, imagine a light clock, a device consisting of two parallel mirrors with a pulse of light bouncing between them. Each round trip represents one tick of the clock. When the light clock is at rest, the light travels straight up and down. But when the clock is in motion, the pulse follows a diagonal route because the mirrors slide sideways during each bounce. This diagonal path is longer, and because light speed cannot change, the pulse needs more time to complete each trip. Thus, the moving clock ticks more slowly when measured by a stationary observer. The geometry of spacetime changes how much time accumulates along the moving clock's path. Physicists describe this effect with a quantity called gamma. At ordinary speeds, gamma remains close to 1, so time dilation is barely noticeable. But as we approach the speed of light, gamma grows without limit, and the passage of time for the moving object approaches 0. Now let's talk about photons, those massless particles that make up light. Special relativity dictates that photons must travel at exactly the speed of light. And here's the kicker. For a photon, the proper time between emission and absorption is 0. It doesn't matter if the photon crosses 1 billion light-years. Along its path, there is no elapsed proper time. This concept is mind-boggling, almost like a philosophical conundrum. It's not that the photon thinks or observes anything. It's a mathematical description, a way for physicists to understand the universe. Photons follow what are called null paths, where spacetime assigns no proper time interval between emission and arrival. Even in curved spacetime where gravity comes into play, the proper time result remains the same. A curved path followed by light is still a null path, and elapsed proper time remains 0. This has practical implications too. GPS satellites, for example, rely on these ideas to function accurately. Without corrections for time dilation and gravitational effects, GPS would become useless within hours. So what does all of this mean? Well, it challenges our very understanding of time and space. There is no universal clock ticking away behind the universe. Each object accumulates time along its own path, shaped by motion and gravity. Light, with its constant speed, marks the boundary of cause and effect. Nothing with mass can reach that boundary, and no signal can cross it faster than light. Along that boundary, time doesn't just become very slow. The proper time between departure and arrival is precisely zero. It's almost as if time itself ceases to exist for light, a concept that boggles the mind and challenges our deepest intuitions. So the next time you gaze up at the night sky, consider the journey of those distant photons, traveling across the cosmos for billions of years, yet experiencing no time at all. It's a humbling reminder of the vastness and complexity of the universe we call home. Thanks for joining me on this journey through special relativity. I hope it sparked some curiosity and left you with a deeper appreciation for the wonders of the cosmos. Until next time, keep questioning, keep exploring, and never stop wondering about the mysteries of the universe.